Good morning. So I want to finish up our discussion of Chapter 8 today and the 3 weeks or so we've been spending on synthetic organic chemistry. And so Chapter 8 has moved us into planning multi-step synthesis and strategies in synthesis. And I want to use this as an excuse also, to talk about the Diels-Alder reaction and the Robinson annulation, both of which get covered in the chapter. So the big picture in synthetic organic chemistry is being able to see how to put complex molecules together. And that means taking a step back from the specific tactics and looking at the strategies that are involved. In other words, focusing on how you build the molecule and not worrying about reagents, worrying about the main carbon-carbon bond forming reactions, initially not even worrying about the functional group transformations. So the idea of retrosynthetic analysis is really, say, thinking backwards. I'll say thinking backwards about synthesis. And in sort of the big picture, you'd say you look at a product, and we'll be taking an example from the non-assigned problems, taking it back to simpler molecules, taking those back to still simpler molecules, repeating as needed, so I'll say etc., and ultimately going to what we will call simple starting materials. And by simple starting materials, I mean compounds that are commercially available or compounds for which there's a known synthetic route that's often been worked out, or that's been worked out. SciFinder and Reaxys end up being your friends in finding good syntheses of simpler molecules. And then the big picture here is, as I said, focus on the strategy, not the tactics. In other words, you can worry about, do you use lithium aluminum hydride? Do you use sodium borohydride? Do you do a reduction and a reoxidation? Do you do a reduction, a partial reduction? You can worry about that later, but the big picture is let's look at how we form the bonds. So I'll say how we form the carbon-carbon bonds. And we use these sorts of arrows that I've shown here to indicate we're thinking backwards. That doesn't mean we're done with the job. That's kind of like showing your work or showing your thinking. Then what we want to do is write the forward synthesis. With reagents, etc. And I wanted to exemplify this process and also talk about a couple of reactions that you should know. We've talked about one before, but not in a synthetic context, the Diels-Alder reaction. and also the Robinson annulation, which came up on a previous homework. And I want us, and again, that's sort of sophomore Chem 51C chemistry, but I wanted us to take a chance to review that. So, okay, let me show you the problem here. The problem is 8.7. And I've written it also on the sideboard because at some point I will be erasing this blackboard, and I wanted to have it up so you could refer to it without having to flip through your notes. So 8.7 is what potentially looks like a very hairy molecule. Here's the molecule. It's a tricyclic system. It's got a cyclohexanone ring on it. It's got another 6-membered ring, and it's got an angularly fused 5-membered ring. So it looks like it might be sort of daunting. Now, in looking at this molecule, I was impressed in looking at it as an example to talk about in today's class, because even though it looked like a very daunting molecule, I saw a cyclohexene ring, and immediately cyclohexene makes me think about a Diels-Alder reaction. So let me show you that backwards. In a Diels-Alder reaction, a diene and a dienophile come together to form a 6-membered ring. And that's the 6-membered ring that we have over here. And what's defining, it's a lousy drawing, I'm gonna fix it. What's defining about this particular example is that we're going to need a 3-carbon tether, 1, 2, 3, to connect the diene to the dienophile. In other words, this is what we would call an intramolecular Diels-Alder reaction. And that looks eminently reasonable. We'll talk more about the stereochemistry. Diels-Alder reactions prefer endo. They're endo what's called stereoselective. And the relationship between this stereochemistry and this stereochemistry comes from the stereospecificity of the Diels-Alder reaction being supramolecular. Now, in looking further at this reaction, I just want to now go ahead and rewrite this so we can see this molecule now, because now we've reduced this to a much simpler molecule. We've reduced it to a molecule that contains a cyclohexenone and a diene. And I just wanted to write that in a linear fashion. So a cyclohexene clues us in that you may have a Diels-Alder reaction. A cyclohexenone clues us in that you might be able to form this molecule by a Robinson annulation. And so again, thinking backwards, I'm going to take this molecule apart, and I'll show you that. And so in a Robinson annulation reaction, we are going to take the molecule apart in the retrosynthetic sense to this ketone and this enone, the enone being methyl vinyl ketone. And so I'll write this like so. So basically, if we want to summarize I'd say cyclohexene clues us in to maybe a Diels-Alder, and cyclohexenone clues us in to maybe a Robinson annulation. And in this week's homework, you have another cyclohexenone, as you did in last week's homework, that lends itself very nicely to coming from a Robinson annulation. All right, I don't want to take a lot of time to review the Robinson annulation. You should have learned this in sophomore organic chemistry, but I want to remind us of the basic idea. The Robinson annulation is a very powerful reaction. It was developed by Sir Robert Robinson. We've already mentioned him. He won the Nobel Prize in 1947 for synthetic organic chemistry. We saw his synthesis of tropinone. The Robinson annulation is the reaction of an enolizable ketone or aldehyde with an alpha-beta unsaturated ketone to give a cyclohexenone. The reaction involves 3 steps. And by 3 steps, I mean 3 broad concepts, not 3 mechanistic steps. The first is the Michael addition of the enolate of the aldehyde. So I'll say the Michael addition of the ketone or aldehyde. To the alpha-beta unsaturated ketone. The second step is an intramolecular aldol to form a beta hydroxy ketone. And the third step is the dehydration of the alpha-beta of the beta hydroxy ketone to the alpha-beta unsaturated ketone. In some cases, the Robinson annulation reaction can go in a single pot. And it's really a beautiful reaction when it does. Let me give you one example. So this example comes from the Journal of Organic Chemistry in 1973. And it's volume 38, page 175. And the example is very nice. If we take this carboethoxycyclohexanone and we just literally cook it up with 1-pentene 3-one with sodium hydroxide or sodium ethoxide and ethanol, we get the bicyclic system, we get the cyclohexenone system. Like so. And this goes in overall 59% yield. That's pretty darn good. So the Michael addition, we can envision forming the enolate here, it adding a new enolate forming, and ultimately protonating that enolate. And so the Michael addition reaction sets us up like so. In a solvent like ethanol with sodium ethoxide, every acidic position gets protonated and deprotonated. This position gets protonated and deprotonated. This position gets protonated and deprotonated and protonated, deprotonated and protonated. This position gets deprotonated and protonated. But there's only one particular reaction that can give rise to a six-membered ring, and six-membered rings are especially thermodynamically stable. And so after the aldol reaction, you get a six-membered ring. Like so. And again, under these conditions, under these equilibrating conditions, all different acidic protons come on and off. The OH gets deprotonated, you get OH minus, it gets reprotonated. The position on this side of the carbonyl, alpha to this carbonyl, gets deprotonated and reprotonated. But only one deprotonation over next to the carbonyl at the more substituted position allows an E1CB elimination to occur to kick out hydroxide anion and eliminate to give you the Robinson annulation product. And so it's absolutely amazing and fantastic, but also scientific fact that if you mix these two compounds together, the cyclohexanone and the alpha-beta unsaturated ketone, that you get in a very decent and respectable yield this cyclohexenone product. So I sent out a more detailed treatment of the mechanism that I did for my sophomore organic class on a YouTube video for problem 7.32. I think I'll queue it up and send it again if you want to spend more time thinking about this chemistry. I take you through all the curved arrow pushing, the deprotonation, the generation of the enolate, the attack, the reprotonation. It's also a good review on curved arrow pushing. I'm a good person in that video. I keep track of my lone pairs all the time, which I don't always do in this class. Anyway, I'll send that out again. All right. So in part because I wanted an excuse to talk about the Robinson annulation, and in part because I wanted to keep the reaction, the menu of reactions in the synthesis of 8.7, of the molecule in 8.7, I wanted to keep the menu of reactions relatively limited to things we've covered in this class, or you should remember from sophomore organic chemistry. I decided that I would go ahead and take a Robinson annulation approach to that molecule. So I want to show you now my proposed synthesis for problem 8.7. So the proposed synthesis that I do, Robinson annulation works great when you have a very stable enolate. And often you can go ahead and get the whole cascade to work in one pot. Very often, though, in a modern Robinson annulation, people dissect the reaction into one or more different pots. For example, an asymmetric Michael addition reaction catalyzed by an amino alcohol or a derivative of proline, a reduced proline derivative to make an enamine. A chiral enamine is one of the tricks that's often used. In this particular case, I didn't think that we could do the Robinson annulation in one pot because we didn't have a very stabilized enolate. So I wanted to break out the Michael addition separately. So at least for cases of this class, I took my absolute favorite conditions, LDA and THF. Remember, LDA makes the less stable, the less substituted enolate if you do it at -78. Methyl vinyl ketone should work well for a Michael addition, followed by an aqueous workup. And remember, the Michael addition gives rise to a 1,5-dicarbonyl compound. So there's our 1,5-dicarbonyl compound. And then we're set up for an intramolecular aldol. All of these positions I'm talking about, all these positions are acidic. But my hope in this particular example was that we would be able to get the Robinson annulation. And that was in part a product of my efforts for keeping this within the class here. So I'm going to write this. I was a little concerned about a different regiochemistry as well, about attack over here. But I figured often synthetic organic chemistry is a little bit of an empirical science where you have to go and try things and try different conditions, as Sebastian well knows in his research project. And so I wanted to take us over to this Robinson annulation product, this cyclohexenone, and then take us with heat through an intramolecular Diels-Alder reaction to the tricyclic system. And I was reasonably confident that we'd get the desired stereochemistry, and realize that this is a racemic synthesis here. You will get both enantiomers, so you will get the molecule where every stereochemistry, every stereocenter is the opposite of what we've written here. All right, so I guess I just want to show you a little bit more about the endostereoselectivity since we do set 4 stereocenters here. So my hope on this reaction is that the diene, here's the diene, and I've tried to draw it in one plane. The diene would swoop in over the dienophile such that the dienophile was pointing under, right? We have a plane here and a plane here, such that the dienophile was pointing under, and then I'm just going to write CH2,3 to show our tether here. And if you go ahead and you envision forming a bond here and forming a bond here, and I try to write the product in as close a shape as I can to the reactants, just so you can see the relationship, we end up with this hydrogen up, the methyl down, a hydrogen up here, a hydrogen up. We end up with this group pointing up. We end up with this group pointing down, and I'll just again draw my tether and say we have CH2,3 as our tether. And so that was my vision on the stereoselectivity. In other words, my hope was that it would go endoselective intramolecular. All right. So that's sort of the good. And now I want to get to maybe the bad or the ugly in my proposed synthesis. But again, I wanted to keep to reactions that we had learned in class. In general, the goal in synthetic organic chemistry is to come with as few steps as possible, or at least that the steps be very efficient and easy to do. Often that means what's called convergence, where you're bringing together fragments. Because we don't have that many reactions that we've used, I didn't have that many tools in our toolbox at this level to set up the diene. And what I envisioned setting up the diene, I figured we could take it back over here, and this gets a little bit steppy. I figured we could take it back over here, and this is again where retrosynthesis comes in, and we're not going to worry about the details. And I figured we'd take it again to an alkylation reaction, so we'd be dealing with reaction of an enolate with an alkylating agent. I'll say enolate alkylation. In practice, if you wanted to do this reaction, this would be a halide or a tosylate. In practice, you might be better off with the acetoacetic ester synthesis, where you use ethyl acetoacetate. You go ahead, it alkylates very efficiently. You then hydrolyze the carboethoxy group and decarboxylate. All right, coming backwards on the diene portion, and again, let's not worry about what X is right now. We didn't have that many reactions in our toolbox for the stereospecific, stereoselective synthesis of dienes. The one reaction that we did have was the Wittig reaction with a stabilized ylide. Remember, I talked about stabilized ylides give trans products, unstabilized ylides give cis products. So I saw this double bond as coming from a Diels-Alder, from a Wittig reaction of the stabilized ylide. But to get to that point, I needed to go ahead and have the ethyl ester here. In other words, we needed to think about the methyl group coming from some sort of reduction of the ethyl ester. Taking this backwards by way of a Wittig reaction, now we can come to the aldehyde, like so. Simpler is always in the eye of the beholder, and there's the question of when you get simple enough And I figured, all right, if we go ahead and we think of that as coming from a Wittig, we can again come back and say Wittig over here. And in general, most people would consider a bifunctional compound, a small molecule with two functional groups in it, to be a simple molecule. So that was my synthesis. So that's the retrosynthetic analysis. As I said, it's bad in a couple of ways. It's bad because it's steppy. It's bad because it has this extra overhead of burning down the carboethoxy group. But this all falls into reactions that we've learned in the class. So that's the retrosynthetic analysis. Now my job is, having worried about the strategy, having worried about the basic ideas of building up the skeleton of the molecule, now I need to choose my reagents and think forward. And if I wanted something that was really simple, I'd probably take 3-hydroxypropanol. 3-hydroxypropanol. I'm going to want to get this OH group out of the way. Ultimately, I'm going to need it to be an alkylating agent. I'm going to need it to be a halide or a tosylate, but I don't want to carry a leaving group through the synthesis. So I'm going to protect it. The organic chemist's go-to protecting group for alcohols is tert-butyl dimethyl silyl-chloride. You put, or is the TBS ether. You put it on with imidazole and TBS chloride. Imidazole is a base. Imidazole is the heterocycle. With 2 nitrogens in it. You saw it in chapter, what was it, 1, where we talked about nomenclature. Anyway, these are the go-to conditions for putting on a TBS protecting group. I'm going to draw our TBS protecting group once so you can see it, and beyond that I'm just going to write TBS. All right, now at this point we're set up for a Wittig reaction. There are many variants of the Wittig reaction. There's the Horner-Wadsworth-Emmons variant of it that uses a phosphonate. But we introduced this variant, which is just fine with the standard phosphorus ylide. You can buy that reagent. You can make it by deprotonation of the corresponding salt of ethyl bromoacetate. And triphenylphosphine. So anyway, now we need to get our ester group. This is a very good go-to reagent. We need to get our ester group to the aldehyde. You can do reduction with dibal. This is a tactical thing. You can do reduction of an ester with dibal to the aldehyde under the right conditions. It kind of sort of works. The dibal forms a tetrahedral intermediate with the oxygen bound to aluminum diisobutyl aluminum hydride. You can do that as the reagent, but honestly, most people just go ahead and they'll burn down with lithium aluminum hydride all the way to the alcohol. So I'll say LDA and THF. Carry out an aqueous workup, and then in another step, do a PCC or Swern oxidation. Remember, PCC and Swern take an alcohol back up to the aldehyde. They don't over-oxidize to the acid. So that would probably be how one would typically carry out this chemistry. Fewer steps is great, but sometimes steps are so easy that it's not worth fussing with. So now we're at the aldehyde. Again, we would build it up with the Wittig reaction. And that should get us our diene stereoselectively. Now, the last thing we need to do to have our diene is we've got to get a methyl group over here. And in class, we've learned one way of taking something that's not in the alkane oxidation state, making it in the alkane oxidation state, and that's the Barton-McCombie deoxygenation that I introduced back a couple of lectures ago. Remember, that's the free radical chain mechanism. And I thought we'll go ahead and use that. So again, we're going to burn this down to the alcohol with lithium aluminum hydride in THF and carry out an aqueous workup. That's going to take us over to all the way to the alcohol. The Barton-McCombie deoxygenation at this point is where I want us to go. And so I'll just write this on the other board. So the Barton-McCombie deoxygenation, we make a xanthate ester. I don't want to go over this again. It's in your notes. We pull off the proton on the alcohol with sodium hydride. We deprotonate with sodium hydride. We treat with carbon disulfide and methyl iodide. That makes a xanthate ester. It's a thiocarbonate ester. And then we treat with tributyl tin hydride and AIBN. And we warm this up. Usually you do this reaction in benzene under reflux conditions. I had some concerns about doing this reaction on paper here. I wanted to stick to things we know, but one of the things that worries me is you're going to generate a free radical at this position. That radical is going to be delocalized over the diene system, which means you may end up having the double bond migrate or even break conjugation in the double bond, but I figured that was pretty reasonable. Lithium aluminum hydride on the tosylate or the iodide or the bromide might be another way to do this reaction. There's also some risk of radical reactions. Sodium borohydride might be another way to do this reaction. All of these, again, you would probably look more in the literature to check what's been done in similar systems and what's worked, and then you'd go into the laboratory. At this point, I want to take off our tert-butyl dimethyl siloprotecting group. Silicon loves fluoride. So this reagent here, TBAF, used in THF with a little water, I'm just going to abbreviate it TBAF, we'll see it again, is a great way to take off the TBD-DMS group. It is the go-to group for that. And that should take us over to the alcohol. At this point, I wanted to take us to our favorite leaving group, and so I figured you could go with a tosylate. I figured I'd use PBr3 to make the bromide, phosphorus tribromide. Phosphorus forms a bond to oxygen. Phosphorus loves oxygen. That makes the oxygen into a leaving group. Bromide attacks. And now we're set up for our enolate alkylation. In practice, I'm not that keen on the idea of making the enolate of acetone. Almost any other ketone I'm fine with. I would actually check the literature to see how well the enolate generation of acetone works, but on paper I thought this would be pretty reasonable. Certainly if we had any other steric group on one side, I wouldn't worry about this reaction. So if we treat with LDA and THF, we should be able to make the enolate. Then if we go ahead and we take our iodide, or bromide, I guess I'm using, that should take us all the way over to the corresponding ketone. Thoughts or questions at this point? All right. So if I look at this reaction, if I look at this retrosynthetic analysis as I've presented it, the good is the Diels-Alder reaction. That is the strategic reaction. You form all of your structure practically at that one point. The bad is the Robinson may be messy. We may get mixtures of products. We may not even get the right regioisomer, and it sort of illustrated the concepts I wanted to illustrate. And the ugly is the steppiness to build up the diene with the desired stereochemistry, in part because we don't have the tools in the toolbox. So I want to show you, this is a synthesis that Sam Danishefsky worked out, and I want to show you, this was published in JACS in 2012, and of course it's always worked out by students in the lab, but people end up associating with the PI, with Professor Danishefsky, who is one of the masters of the Diels-Alder reaction, Danishefsky. So here's his synthesis. So he goes at a slightly different strategy, doesn't use the Robinson annulation. It's really very nice. So his idea, we're going to come to this iodide in a second. His idea is to go ahead and have one more carbon in the chain. So we had a 2-carbon chain and then used an enolate disconnection to ultimately make what would be the ketone that would make the cyclohexanone. He wants to make an organolithium at this position and add it in directly. Reactions that you've learned for making nucleophiles, metal nucleophiles, would be to use lithium metal to make the organolithium compound, or to use magnesium to make the Grignard. Both of those work fine. In practice, what the Danishefsky group did was a halogen metal exchange reaction. Tert-butyl lithium is super basic. Almost any other alkyl lithium is less basic than tert-butyl lithium. So they generate the tert-butyl lithium. You don't isolate it, you generate it in situ. Here's where the really clever part of their strategy comes in. They go ahead and they add it into cyclohexanone, and they carry out an aqueous workup. And the overall result is, as you would expect, a 1,2 addition. And here's a reaction that we haven't learned. If you have a tertiary allylic alcohol and you oxidize it with PCC, or chromium trioxide, you get an allylic conversion. You can think of this as going through a chromate ester and a sigmatropic rearrangement of the chromate ester in a standard oxidation reaction. The overall result is that you get the cyclohexanone like so. And this is really brilliant because it makes our synthesis very convergent, and it makes it fewer steps. So the synthesis I proposed had this sort of stepwise building up of the chain, what's really good in synthetic organic chemistry is to have the fewest number of linear steps. And here we go ahead, we bring two halves together, and you're going to see he's going to do the same thing on the diene synthesis. We bring two halves together, a 6-carbon piece that all at once gives us our cyclohexanone component, and this piece over here, which gives us, I guess it's an 8-carbon piece, that gives us our diene component all together. Now, the key reaction here was the Diels-Alder reaction. That was the key in the strategy I proposed. That's the key in his strategy. In reducing this to practice, it works pretty darn well for forming this level of complexity. They go ahead and they heat their diene cyclohexanone up at 200 degrees in 62% yield. They add a little bit of a radical scavenger. They add BHT there to prevent oxidation or free radical reactions. And it works pretty darn well. Of course, it's a racemic synthesis. I'm only drawing one enantiomer. That's fine. It works pretty darn well you go ahead and you get in 62% yield the Diels-Alder reaction. Now, one of my concerns was whether we would get endoselectivity. And he gets just thermal without Lewis acid catalysis or anything to, so I got to get my double bond there, and without anything else, they get a 2.4 to 1. So this is the endo diastereomer. And now I'm going to draw the exo diastereomer, and they form in 2.4 to 1 ratio. So the Diels-Alder reaction is pretty stereoselective. The exostereoselectivity comes from, instead of the cyclohexanone being tucked under the diene, instead of the carbonyl being tucked under, it's pointing out in the other direction. That gives rise to the opposite stereochemistry at the ring junction. And again, I've only drawn one enantiomer. And so I thought that was pretty good. The other part of the Danishefsky synthesis that I liked very much, and it resonates with me because I developed the Chem 160 lab course, was the synthesis of the diene. And one of the experiments, who's taken Chem 160 here? One of the experiments we do in Chem 160 is a Suzuki cross-coupling reaction to set up a diene stereoselectively. So I want to show you that reaction. And what I'm going to do, we're not going to talk extensively about the Suzuki reaction. And as I said, I think for three weeks or so on synthesis, we just have, there's only so much we can do in terms of new reactions. But I know that several people were eager to go ahead and learn more about organometallic chemistry. So at the end of today's lecture, when I go back to my office, I'm going to email out a lecture that I gave, just as optional if you're interested, that I gave my Chem 51 class in the spring, Chem 51C, a few years ago. And it gives a pretty nice coverage of the Suzuki reaction and other organometallic reactions. So in the Suzuki reaction, we're going to form the diene by combining the two halves. So we are going to form this bond over here by combining a organoboron compound, a vinyl boron compound, with a vinyl bromide. And I'll show you the setup for this. So we're going to generate the organoboron compound like so. We do it by a hydroboration. You've seen hydroboration in sophomore organic chemistry. In this particular case, we use the reagent catechol borane This is the same reagent we use in the Chem 160 lab course. Catechol-borane does a hydroboration. It's a syn addition across the triple bond. And what's nice is you can isolate the organoboron compound. And then the key step here is a Suzuki reaction. So we're going to take propenyl bromide, and we're going to go ahead and do a Suzuki cross-coupling where we treat this with a palladium catalyst. We treat the mixture of the organoboron compound, the vinyl borane, and the vinyl bromide with tetrakis triphenylphosphine palladium, and you use a catalytic amount, and sodium ethoxide. So I'll send out a video where I talk more about this reaction. What happens in the Suzuki reaction is then you go ahead and you generate the double bond like so. And that very nicely brings together the diene component of the reaction. And you notice we get this element of convergence here. I mean, it's sort of linear, but it's convergence in the sense we're putting the molecule together in sort of one big, from two components forming this strategic bond. Finishing up, it's very similar to what you've seen. He goes ahead, he treats with TBAF in THF water. That's going to take us over to the alcohol. And then he makes the iodide by treatment with triphenylphosphine and iodine and imidazole. Basically, figure it this way, make an iodide or make a bromide. You could use phosphorus and red phosphorus P4 and I2. He uses these conditions. The overall result, it's all the same basic idea. You make an electrophilic phosphorus, a phosphonium. The phosphorus gloms on, forms a bond to the alcohol. The alcohol becomes a leaving group. Iodide does displacement. That takes you to the iodide. Anyway, that's the Danishefsky synthesis, a very nice synthetic reaction, very nice synthetic series. I particularly liked, in addition to the Diels-Alder, the allylic oxidation part that we haven't had in class and won't have. All right. We will pick up next time talking about Chapter 9. We'll talk a little bit more. It's sort of on mechanism and how reactions occur, of a few practical pointers, and then we'll move into Chapter 10 on spectroscopy.